Hi children and hi everyone. In previous video I explained about the electric field intensity at a point on the equatorial line. So in this video I am going to explain about the one more small topic but it is important: electric field lines and electric flux. Electric field lines means they also called as the electric lines of force. So in this video I am going to explain about the properties of electric field lines and what is the electric flux. Children, if any one of you just now only you are watching my channel, then subscribe to my channel and press the bell icon to get the latest notifications. Okay children, now I am going to the topic here. What is mean by electric field line? What is mean by electric field line? That is the question here. So I already explained what's that. What is mean by electric field? Electric field is nothing but the space around a charge which can its influence. The space around the charge which is in its influence is called electric field. So electric field line, that means in that electric field we are drawing some line. That line is what we have to go discuss. For example, this is the one charge plus q, and here I am drawing the space around the plus q charge. Now it is the electric field. Up to this space that should be having its influence. That's why it is an electric field of intensity. I am taking now, that is E. E is the electric field intensity of that field. In that field, if we can keep some other charge, we are taking Q naught, unit positive test charge, unit positive test charge. Then the path followed by the unit positive test charge in that field should be called as electric field line. Simply what you have to say, path followed by the unit positive test charge in an electric field is called electric field line. Clear? Here electric field lines are completely imaginary lines. So here now in this case, how the electric field lines are there and what are the electric field lines of, what are the properties of electric field lines of force? Let us see. Here in our textbooks also they clearly given some diagrams about the electric field lines. Here if you can take some positive charge, the electric field line should be shown like this. Clear children? So here for positive charge, electric field lines are showing like this. That means here radially outwards we can represent the electric field lines radially outward direction for positive charge. In case of positive charge, electric field lines are moving outward. And if you can take negative charge, for that we can represent the electric field lines should be radially inwards. Now this is the isolated negative charge. So these are what? Electric field lines. Electric field lines of negative charge. Clear children? So we can represent like this. Here you have to observe, look at the arrow marks. For positive charge we are representing the electric field lines are, they are moving away. That means they are outward. But positive charge, that should be like that. For negative charge, what you observe, you have to observe here arrow marks. Those are radially inwards. So here these are the electric field lines for positive, isolated positive charge, and this is for isolated negative charge. If we can take a dipole, for them how we can draw the lines of force? Let us see here. So now this is a positive charge and this is a negative charge. Clear? We are showing like this. This is what? Dipole. Here what you observe? In this case you have to observe, for positive charge how we can represent them? Radially outward. Radially outward. Clear? And now for negative charge how we can say? Yes. Clear children? Watch carefully. For positive charge, here we are showing that the arrow marks are radially outward. Here also radially outward. And now in this case, what you have to say? Radially inward. Clear? That means simply what you have to say in this case, the electric, when we have some dipolarities there, the electric field lines are going from positive charge to the negative charge. So we have one important difference between the magnetic field lines and electric field lines. Later we discuss. So here now I am drawing like this. Here radially outward, radially outward. So here these are the electric field lines. Electric field lines of a dipole. Got children? Here what you observe? The electric field lines are moving from positive charge to the negative charge. That means what you have to say? Here there is some attraction between these two there. Here that is what we call simply electric field lines will be having some longitudinal tension. Longitudinal tension means that is nothing but force of attraction. Okay, clear? Plus, and this is the minus. They are unlike charges. That's why here they should be attracted together. Those should be shown by these two field lines. And now here some of these electric field lines are there. Here they are also moving like that, but they will occupy the more space. Here these two field lines are coming from positive to the negative, and these also reaches the negative charge, but they will occupy the more space. So it is not sufficient to draw this remaining one. That's why we are simply showing like that. So this is the electric field lines regarding the dipole. And now if you can take electric field lines for same type of charges. Same type of charges. Here I am taking, this is a positive charge and this one also positive charge. Clear? Now here we are showing like this. Here we are showing like this. Here both are, now here what you have to say? Both are positive charges we are taken. Both are positive charges. Here arrow mark must be always outwards, radially outwards. Here what you have to observe, if we can take plus and plus, they are like charges. Like charges always repulse. That's why here the field line should be going like this. So they are not coming towards each other. They are not attracted. They are repulsed. That's why here what we say, in this case we have to observe they are repulse each other. Repulse each other. That means here there is some lateral pressure between the electric field lines. Lateral pressure. The lateral pressure between the electric field lines, that is the cause for the repulsion. For longitudinal tension there is some attraction. For field lines there is some longitudinal tension that will represent the force of attraction. But in this case what I am telling, there is some lateral pressure will be there. That should be cause for the repulsion of like charges. And now here this is what we say, these are the electric field lines for two equal and same type of charge. Here these two charges what we are taken, they are equal and same. Plus 5 plus 5. Plus is same, plus 5. If you can take plus 5 minus 5, both are different. But I am taking here plus 5 coulombs, plus 5 coulombs. Then equal magnitude of same charges, those should be having repulsion should be like this. and the field lines should be shown in the diagram. And now here, if you can go for other, I am taking now unequal charges and same. Unequal charges and same. Clear? This is the I am showing. So here, unequal charges but same type of charges. In this case, we will say here, we will draw the more electric field lines for the high amount of magnitude of charge. Clear? Now like this. So here how we are saying this is a very high magnitude of charge. How we are saying, for that we have more magnetic lines are there. Sorry, more electric field lines are there. For this, less electric field lines are there. That means the charge which is having more amount of magnitude, that should be having more field lines. Clear? For this one, here plus, then also it is repulsion. But in this case, what I have to say, we will draw for the more field lines for high magnitude of charge. So children, in this way, the same figures will be in your textbook, will be there. That's why here you have to once check them. So here now we go for properties of electric field lines. Properties of electric field line. What I told you, electric field line means what? The path followed by the unit positive test charge in an electric field is called electric field line or electric line of force. The path followed by the unit positive charge will be called electric field line or electric line of force. Clear, children? Now here I am going to explain here properties of electric lines of force. Electric lines of force, and they also called as electric field lines. Electric field lines. The terms are different but the meaning is same. Properties of electric lines of force or electric field lines. So the first thing is here, electric field line. Clear? If we can draw a tangent at any point on the field line, that will give the direction of the electric field. What is that? Direction of electric field. For example, here in the same, here I am taking, this is a dipole here. Now I am showing like this. This is the direction of one electric field line. At this point, if you can draw one tangent line at any point on the field line, if you can take a tangent or if you can draw a tangent, that will give direction of electric field. Direction of electric field. That is the first property. Clear, children? The thing is what? If you can draw any tangent at a point on the field line, at any point you can draw tangent on the field line, that will use the direction of the electric field. Got, children? This is the first point. And now here the tangent gives direction of electric field. Direction of electric field. This is the first thing. And now here electric field lines are open lines. Electric field lines are open lines. There is difference between magnetic field lines and electric field lines. So in case of a magnetic field line, clear, in a magnetic field line, generally we know that the magnetic field lines for a magnet, if you can show like this, outside the magnet they are moving from north to south, but inside the magnet they can move from south to north. Clear? Already it is in 10th class, it is there, I think so. Here magnetic field lines are closed lines because outside the magnet they can move from north to south, but inside the magnet they can move from south to north. But in this case of electric field lines, they can move from only positive charge to negative charge. The electric field lines are starts from, for example here, same example, this is the dipole, plus or minus, we are showing like this. Here electric field line starts from positive charge, that should be goes to the negative charge, and we are showing again like this only. radially outward here, but if you can keep like this, it is a closed line. But according to properties, we have to always represent the electric field line should be in radial outwards. That's why here, in case of a dipole, it is moving from positive charge to the negative charge only. Again, there is no moving from negative charge to the positive charge. That's why electric field lines are open lines and magnetic field lines are closed lines. So this is the second property. Electric field lines are open lines and they can move from where to where? Plus Q charge to the negative charge they will move. Clear? And next thing here, these electric field lines are completely imaginary lines. Imaginary lines. And they are in the shape of curved lines. Clear? Imaginary lines means it is nothing but there is no physical existence for the electric field lines. And now next, fourth one. Children, this is a very important for 2 marks question in your examination point of view for an IPE. Electric field lines never intersect each other. Never intersect each other. This is the another important point, children. Electric field lines never intersect each other. Clear? So what is the reason for that? Why they are not intersect each other? That means here reason is there. That is, I am simply showing here. So this is the plus and this is the minus here. We are showing like this. And at this point, for example, I am showing like this. At this point, what you observe? Both are intersect. Clear, children? So this is the one electric field line and this is the another one. If they can intersect, there is chance to draw the two tangent lines. Clear, children? Watch carefully. Here, this is the one electric field line and this is the another electric field line. Both are intersect at this point. Clear? What I told you, at a point on the electric field line, there is chance to draw the one tangent line that can represent the direction of the field. Clear? At this point of intersection, there is chance for to draw the two tangent lines. That means at the point of intersection, there is possibility for to draw the two tangent lines. The tangent line must be represents the direction of the field. How we can say that? The only what is meant by electric field line? Electric field line is what? The path followed by the positive charge. Is it possibility to move the same positive charge in two directions at a time? Tell me, for us also, it is not possible to move in two directions at a time. We must be walk in one direction only. Clear? Is it possible to move in two directions, east and west at a time? No, not possible. Like that, while the electric fields are intersect each other, at the point of intersection, there is possibility for the to draw the two tangent lines. That must be what? The field must be in two directions, but it is highly impossible. That's why what we have to conclude is the electric field lines are never intersect each other. Clear, children? Electric field lines are never intersect each other because if they can intersect at a point of intersection, the field must be in two directions. It is highly impossible. Clear? That is the point here you have to remind. And now, here next thing, in a non-uniform electric field, for example, here I am showing, look at this one. For example, this is the one electric field. Clear, children? Watch carefully. This is the one electric field. So that should be like a plane surface. Clear? And now here we are taking, this is like this. So in this case, it is the one arbitrary surface, and this is the plane surface. Clear? Plane surface and arbitrary surface, or any like closed surface. And now in this case, what you have to observe, just see what I am drawing here, all are the electric field lines. These are what? All are electric field lines. In this case, you have to observe very clearly, all electric field lines are in same direction. All electric field lines are in same direction, and they should be separated by equal distances. The separation between two electric field lines is nothing but magnitude. What's that? Magnitude. And they should be in same direction. That's why here now it is called uniform electric field. What is mean by uniform electric field? The electric field which consists of electric field intensity is same at every point in the field, both in magnitude and direction. That should be called electric field, is what we call uniform electric field. Clear? In which electric field the electric field intensity is same both in magnitude and direction. That should be called here uniform electric field. The uniform electric field is here nothing but we can simply represent that by using the field lines should be like this. That means here the field lines are separated by equal distances. Equal distance means that is the magnitude, and arrow marks represents they are in same direction. That's why it is what we say simply, it is uniform electric field. So in the case of magnetic field also we are showing like that only, but in this case we are simply it is what is uniform electric field. In uniform electric field, the field lines are separated by equal distances and all are should be in one direction. That is the uniform electric field. Now I am going to this one. Here in this case, the electric field lines are very close. The same electric field lines in the field, at some places they are crowded together. Then that is the stronger region of field. Non-uniform electric field. In electric field, the electric field intensities varies from point to point or some region to region. That is what we call electric field intensity is not uniform. That's what it is called non-uniform electric field. Clear? Electric field is same, that is the uniform electric field. If electric field intensity is not same, that is the non-uniform electric field. So that should be represented by like this. Here in a electric field, in an electric field, at some regions electric field lines are close together. That region is the strong region. At some places they are separated by some distance. That is the weaker region. Clear? So simply here we can say that in electric field lines are, if they are in same direction and separated by equal distance, that is the uniform electric field. In an electric field, at some places the field lines are very close together and some places they are separated by some distance, far off the distance. That is what you say non-uniform electric field. Clear? And that is the next one. And next thing is it is here based upon, for example, here two electric fields are there. In electric field A we have more field lines. In electric field B we have less number of lines. Two electric fields are there. One is the A and next electric field is the B. A consists of more number of field lines and B consists of less number of field lines. Then the electric field which has more number of lines, that is the strong electric field, and the field which consists of less number of electric field lines, that should be considered as what we say weak electric field. That means based upon the number of concentration of the electric field lines we can decide that whether the field is strong or weak. Clear? And next thing is what you have to say, I already told you. What's that? There is some longitudinal tension between the electric field lines that can represent the force of attraction. There is some lateral pressure acting on the field lines. That should be what we call repulsion. So all these are the properties of electric field lines. So watch carefully all the properties without skipping. Clear? The first thing is what? Electric field lines are imaginary lines. Next thing is what? If you can draw a tangent line on the field at any point on the field line, that should give the direction of the electric field line. And electric field lines are the open lines. They are moving from positive charge to the negative charge. And electric field lines are never intersect each other. If they intersect, at the point of intersection, the field must be in two directions. But it is not possible. And electric field lines are, if they are very close together, that should be what we call stronger region. If they are separated some distance, that is the weak region. If the electric field lines are separated by equal distances in the same direction, then what did you say? That is the uniform electric field. If there is some force between the field lines along the longitudinal, that should be what we show, that is the force of attraction. If there is some lateral pressure between the field lines, that should be what we say, repulsion. So this is the information about the electric field lines. So next we go for electric flux. What is meant by electric flux? Let us see here. This is the, I am taking now, it is the uniform electric field. What is that? Uniform electric field we are taking. So that means I am taking it is a plane surface. What is that? Plane surface. Clear? Electric flux is nothing but the number of field lines passing through the particular area is called electric flux. For example, just imagine, now this is the one water source, and out from that we arrange some pipe. Then in that water, some of the water is going outside through the pipe. Here the pipe entrance is there, that should be like area. Through that area some water is going, like that is the flux of the mass which is going outside. Clear? In the same manner, if you can take an electric field, in that electric field you have to select particular area, then the electric field lines which are passes through that particular area is called electric flux. What do you call? Electric flux. Got my point, children? For example, here this is a one uniform electric field. In that we are taken now here, this is the one particular area, this is the surface actually, and if you can take, this is the area vector A, then it will make some angle theta. This is what? Direction of the field. Clear? This is the one particular area, and I am showing this is the area vector like this. The area vector will make some angle theta with the direction of the electric field. Then the flux can be written as pi is equals to EA cos theta. Clear? What is theta? Theta is the angle made by the area vector with the electric field direction. Then flux can be written as pi is equals to E cos theta. This is the expression for now flux passing through a particular area when that vector can make some angle theta. So in this case, simply you can write theta is equals to 0 degrees. Then what do you write? Pi is equals to, what do you write, Nana? Pi is equals to EA cos 0. Cos 0 value is 1. Then pi is equals to E into A. Now the flux is maximum. That should be shown like this. How we can show that? In this case, if it is the direction of the electric field and area vector also in the same direction. Area vector is, so here what I am showing, this is the electric field direction. This is what? Electric field direction. And this is electric field direction, and area, this is what? Area vector. Electric field intensity and area vector both are in parallel, then obviously what you have to say? Theta is 0. When theta is 0, flux will be maximum. That means the area will allow all the lines through them. Clear? And for example, now I am showing like this. Look at this point here, children. Now I am showing this is like this. So then what it is? How much angle? 90 degrees. How much angle? 90 degrees. Then what you say? When A is perpendicular to E, what you write? Pi is equals to EA cos 90. What you write? Here cos 90 is what? 0. Flux will be 0. Clear? So this is about the simply electric flux. The number of field lines passes through a particular area, then what you have to say? That is electric flux. If the area is in the same direction of electric field, the flux will be maximum. If the area is in perpendicular to the electric field intensity direction, that should be here what you have to say? The flux, there is no flux, or flux is minimum. Got, children? So here in this case you have to identify that when pi is equals to EA, then what, right? We have equation is there. Here what you have? Pi is equals to EA, then E is equals to what, right? Pi by A. E is equals to pi by A. So here from this also we can define the electric field intensity. Generally what we have? Electric field intensity, what we have? E is equals to F by Q. E is equals to F by Q, we have formula is there. Now in this case E is equals to F by Q. But here in terms of the flux, what, right? Pi by A. Electric field intensity can be defined as pi by A. Simply how we can define? The flux available in particular area. The flux available in particular area is called electric field intensity. The flux available or the amount of flux in a particular area is called electric field intensity. So here now in examination point of view, for you have what is the dimension formula and units of flux. Dimension formula and units of flux. And here flux is scalar vector. Flux is scalar vector. So here what, right? A dot B is equals to what, right? Mod A mod B cos theta. What it is? It is a scalar. Flux also scalar here. In this case now here I am writing pi is equals to E into A. Already E means what? F by Q. F by Q unit is what? Newton for coulomb. What's that? Newton for coulomb. And area is what? Meter square. Meter into meter, meter square. That's why the units of flux, what you write? Newton coulomb into meter square. This is the units for electric flux. What is the unit of electric flux? Newton coulomb for meter square. Clear? And now here what is dimensional formula? Dimensional formula. What is dimension formula of E by E is equals to F by Q? For what is right? M L T inverse 2 by here I is equals to Q by T, then Q is equals to IT, then what do you have? A into T, A into T, then what do you have? M L T inverse 3 A inverse 1. That is the electric field intensity. I am writing now here E M L T inverse 3 A inverse 1. M L T inverse 3 A inverse 1. M L T inverse 3 A inverse 1. And for area what you write? L square. Then what you write? M L cube T inverse 3 A inverse 1. Clear? Dimension of flux, simply we have E is equals to F by Q. F means what? Force. M L T inverse 2 by Q means what? Charge. For charge what you have? I is equals to Q by T. Q is equals to IT. For current what you have? Ampere. Time T. Then I am writing M L T inverse 2 by AT. Then what do you get? M L T inverse 2 A inverse 1 T inverse 1. That means what we get? T inverse 3. Clear? That's why I'm writing here M L T inverse 3 A inverse 1. And now into A means what? Area. L into B, like that. So then what do you get? L square. Then what do you get? M L cube T inverse 3 A inverse 1. This is the dimensional formula for flux. So this is the information about the electric flux and definition and formula and dimension formula and units when the flux is maximum and the flux is minimum. And now we have one special thing, it is there. So here we are using the formula pi is equals to Ea cos theta. Pi is equals to Ea cos theta. When we can use that one? For uniform electric field, that should be belongs to one plane surface. Plane surface. If you can take a arbitrary surface or non-uniform electric field simply. So then we go for that. Pi is equals to integral E dot ds. This is the electric flux for one arbitrary surface. Pi is equals to E dot s. Here ds means nothing but this is a small element. What is that? Small element of ds. And that should also make some angle theta with the electric field. Clear? It is the electric field direction and this is that element ds that will make some angle theta. For arbitrary surface, the flux will be calculated like this by using the formula pi is equals to integral E ds. So for example here, if you can take the small element, I am writing now here d pi is equals to E dot ds. E dot ds. This is the flux available particular element ds. E dot ds, that is the dot product. What that? E ds cos theta. E ds cos theta. When we are taking plane surface, pi is equals to Ea cos theta. If you go over arbitrary surface, in that we are taking small element ds. For that what do you write? E ds cos theta. So that is only, this is I am writing for only this one. If you want to get the total surface area, for that you have to integrate on both sides. Then what do you get? Integral E dot ds. So here if you are taking integral means that should be belongs to entire surface. So children, so this is the information about the electric field lines and flux. I hope you understand. If you can understand this topic, like, share and comment the video. So if you want get notifications from my channel, for that you must be subscribe my channel and press the bell icon. So I hope you understand. Bye children, we will meet in the next video with another topic. Bye, take care.